Did you know that the universe is expanding? And not only that, but is it expanding at a rate that it's accelerating? Today, we're going to delve into the mysterious world of dark energy. When we talk about the expansion of the universe, we are referring to an incredible phenomenon that occurs on a large cosmic scale. But first of all, we need to understand the origin of this expansion. Imagine that the universe began with the Big Bang, an explosive event that happened about 13.8 billion years ago. Since then, everything in the universe has been moving away from the center point of this event. A popular analogy for understanding this is to imagine the universe as the surface of a balloon being inflated. As the balloon expands, the dots, or galaxies, on its surface move away from each other. However, it's not the balloon's material or the galaxies that are expanding, but the space between them. The most intriguing thing is that this expansion is not constant. We found that the rate of expansion is indeed accelerating. Initially, after the Big Bang, the universe expanded at an extremely high rate, then slowed down due to gravity, but for still mysterious reasons, it started to accelerate again. And to clarify a point, when we say the universe is expanding, we don't mean it's stretching like a rubber band. Instead, new spaces are being created between galaxies, causing them to move away from each other. This idea was reinforced when we observed distant galaxies. They appear to be moving away from us, and the further away a galaxy is, the faster it appears to be moving away. This is the backdrop for our journey today as we delve deeper into the mysteries driving this expansion, dark energy. As we observe the universe, we find fascinating phenomena that are true cosmic gems. One of these phenomena are supernovae, stellar explosions of an almost incomprehensible magnitude. Among supernovae, there is a very special category known as Type Ia supernova. These are not just ordinary stellar explosions. They are precise and consistent events that occur when white dwarfs, remnants of stars that have already exhausted their fuel, steal matter from a companion star until they reach a critical mass and explode. What makes these supernovae so special is their remarkable consistency. Type Ia supernovae have near-standard luminosity, which means that by looking at how bright they appear to us from Earth, we can determine how far away they really are. In the late 1990s, astronomers were observing these supernovae in distant galaxies, hoping to understand more about the universe's expansion. What they found was surprising. Instead of the supernova being where they expected, they appear to be farther away. This suggested that the expansion of the universe wasn't just taking place, it was accelerating. And this acceleration could not be explained by visible matter in the universe alone. These observations of Type Ia supernova were instrumental in leading us to the idea that a mysterious invisible form of energy, which we later called dark energy, could be behind this acceleration. Imagine a universe where galaxies are moving away from each other at a rate that seems to defy the laws of physics as we know them. This is our universe, and to understand this mystery, we enter the realm of dark energy. When we talk about the contents of the universe, the normal matter we know, stars, planets, ourselves, only makes up about 5% of the universe. Another 27% is dark matter, an invisible substance that we can only detect through its gravitational effects. But the silent giant, occupying about 68% of the universe, is dark energy. So what exactly is this dark energy? In simple terms, it is a form of energy that permeates all of space and is primarily responsible for accelerating the expansion of the universe. Unlike the gravitational force, which tries to pull things closer together, dark energy appears to be pushing galaxies further away from each other. The truth is, we're still trying to figure out exactly what dark energy is. Its effects are clear, but its nature remains shrouded in mystery. We know that it does not emit, absorb, or reflect light. It doesn't interact with the fundamental forces of the universe the way normal matter does. The introduction of dark energy showed us how little we really know about the universe. As we continue our quest to unlock its secrets, it remains one of the greatest enigmas of modern science. The terms dark energy and dark matter may seem similar, but they are profoundly different concepts in the universe of cosmology. Both are invisible to our eyes and instruments, but their effects are tangible and crucial to understanding the universe. Let's start with dark matter. It is believed to be composed of unknown particles that do not interact with light or any other form of electromagnetic radiation. We can't see it directly, but we know it's there because of its gravitational effects. For example, stars at the edges of galaxies move faster than expected, suggesting the presence of more mass exerting gravity than we can see. Now, dark energy is an even more mysterious entity. Rather than clumping things together like dark matter, dark energy is driving an acceleration in the universe's expansion. It acts against the gravitational force, causing distant galaxies to move away from each other at an increasing speed. While both are fundamental to our understanding of the universe, dark matter and dark energy have distinct functions and characteristics. Dark matter acts as gravitational scaffolding that helps form the structure of the universe, while dark energy appears to determine the ultimate fate of the universe, driving its accelerated expansion. If the universe were a cosmic dance, dark energy would be the silent conductor, dictating the pace of expansion. But how exactly does this invisible entity shape the fabric of space-time? The history of the universe's expansion is fascinating. After the Big Bang, the universe began to expand at a rate that it initially slowed down. However, for reasons that still baffle scientists, this expansion began accelerating about 5 billion years ago. And dark energy is the prime suspect behind this acceleration. Dark energy acts almost like a pressure that pushes space to expand. When we look at distant galaxies, we notice that they are not only moving away from us, they are also moving faster and faster. This implies that something is working against gravity, the force that would naturally try to pull things back together. Without the presence of dark energy, the gravity of all the mass in the universe would gradually slow down the expansion. However, with dark energy in play, the expansion curve not only flattens out, but actually slopes upwards, indicating acceleration. The impact of dark energy on the future of the universe is the subject of intense research and debate. One of the proposed theories, known as the Great Freeze, suggests that if the accelerated expansion continues, eventually the galaxies will move apart so quickly that they will no longer be visible to each other. The universe will become cold, dark, and isolated. Behind the veil of the unknown, scientists have proposed several intriguing theories to explain the nature of dark energy. Let's dive into some of the more dominant ones and what they imply for our universe. When looking at the composition of the universe, about 68% of it is dark energy. But what is this invisible and mysterious force? Einstein, in his original equations of general relativity, introduced the cosmological constant to keep the universe static, a concept he would later call his biggest mistake. However, this constant could be a representation of dark energy, acting as a pressure that accelerates the expansion of the universe. Unlike the cosmological constant, which is static, quintessence proposes a form of energy that can change with time and space. It is as if the universe were immersed in a dynamic field, and the energy of this field is what drives the accelerated expansion. Some scientists question whether our understanding of gravity, as described by general relativity, is complete. Perhaps dark energy is an illusion, and what we are seeing is the result of gravity behaving differently on cosmic scales. While the cosmological constant is currently the most accepted theory, especially in agreement with the Planck satellite observations, the quest to fully understand dark energy is far from over. New observations and experiments in the future may lead us to deeper understanding or even new theories. If dark energy is so abundant and influences the universe so strongly, why is it so difficult to detect it directly? Let's explore the monumental challenges scientists face in this quest. Unlike ordinary matter, which interacts through fundamental forces, such as gravity, electromagnetism, dark energy appears to have no significant interactions except through gravity. This makes it extremely elusive for our instruments. To indirectly detect the influence of dark energy, we need to look at large-scale structures in the universe. This means that, instead of experiments in laboratories, we rely on astronomical observations of distant galaxies and the cosmic microwave background. Despite technological advances, we are still at the beginning of developing instruments sensitive enough to detect or measure dark energy directly. However, each year new missions and experiments are being planned with this goal in mind. Just like explorers of the past who ventured into uncharted lands with rudimentary tools, today's astronomers are on the frontiers of knowledge, seeking to understand the elusive. The journey to detecting dark energy directly is a difficult one, but it's a challenge the scientific community is eager to take on. Technology is always evolving. Soon, we will launch more advanced telescopes with the ability to capture even more detailed images and data of the universe. These instruments will allow for a deeper look into the expansion of the universe and the role of dark energy in that process. While space is the main stage, on Earth we also conduct crucial experiments. Underground labs are trying to detect candidate particles that could explain dark energy. Each experiment brings us closer to possible answers. The quest to understand dark energy is truly global. International collaborations, combining brilliant minds and resources from around the world, are leading the way in breakthrough discoveries. In addition to direct observation, physicists are improving theoretical models and using supercomputers to simulate the universe. These simulations help predict dark energy behavior and validate our theories. Public interest in science and the cosmos has never been higher. By educating the next generation and sharing discoveries with the public, we fuel passion and curiosity, inspiring future astronomers, physicists, and informed citizens. In the vastness of the cosmos, we are constantly reminded of how little we really know. Dark energy, that mysterious component that drives the expansion of the universe, serves as a tangible symbol of our eternal quest for knowledge and understanding. If you were inspired or learned something new today, please like this video and subscribe to our channel. By doing so, you not only support our work, but also become part of a community that values discovery and exploration.